Okay, so this is kinematics session number 4. So in the last couple of lectures, we have looked at motion along a straight line, and in particular motion along a straight line with uniform acceleration, and vertical motion as a special case of that. Now, yeah, it's okay, but all batches are at that same position, Vinith, so don't worry. So in all batches, we have completed up to the portion of the third major test, wherein you had kinematics along a straight line. So today we will start the next part of kinematics, which is in general, we will talk about kinematics in 2 and 3 dimensions. And particularly, we will start with the application of this in projectile motion. So first of all, when we are talking in 2 or 3D, we talk about the vector parameters. Okay. So our reference frame becomes a 3-dimensional coordinate frame in general. No, this is Manya, this is a continuation of kinematics 1 only. Kinematics 2 will be after completion of this part and when we start relative motion part. Okay.
Okay.
So you will find all the explanations and related problems to this part in the same module that you are currently doing, module 1 in physics, which will have that kinematics portion. Okay. So the reference frame, if you're talking about 3D system, so the reference frame is a XYZ Cartesian system. Okay. And the position of any object or any particle, which in my diagram looks like it's a point on the XY plane, but you have to imagine that it's actually in 3 dimensions. So the instantaneous position is represented by a vector joining the origin with that position of the particle. So the first of the vector parameters is defined by position vector denoted by the symbol R. Similarly, now if a particle moves from one point to another point, the displacement defined as a vector. So let us say if our given particle moves in a certain amount of time from some initial position to some final position, so let's say this is where the particle was initially at time t1, was located at position r1, and from there on it's moved by whatever kind of path to a new position at time t2 over here. So the new position is given by the new position vector r2. then we know that regardless of what path it has taken, the displacement during this time is defined as the vector joining the initial position to the final position. In this diagram, you can see that the vector joining the old position or the old point where it was located to the new point, that one is called the displacement vector. So displacement from t equal to t1 to t2 will be defined as r2 minus r1. So this becomes a vector definition of displacement, or we can say that S is equal to delta r. That is a change in the position vector. Okay, so these are the first two of the vector parameters. If a particle is located at coordinates x, y, z, then its position vector is given by the relation xi cap plus yj cap plus z k cap, or it is nothing but the vector joining the origin of our coordinate system with the instantaneous position p. Now, in a certain time, if the particle moves from one point to another point, such that the position vector was r1 earlier and now it has become r2, then the displacement is the vector joining the initial position to the final position. Okay. The displacement, as you can see, it is the vector joining the initial position r1 at t equal to t1 to the final position r2 at t equal to t2. So when we draw this vector, you can see that it comes out to be the vector difference of r2 minus r1. That's how the definition becomes this way. Okay. So you can also see that how there is a sort of symmetry in these definitions. In one dimension, we had seen position was defined by a single coordinate x, and displacement was defined as x2 minus x1. So in three dimensions, or in general, position is defined instead of a single coordinate, it is defined by a position vector, which has all three coordinates x, y, and z. So displacement, instead of delta x or x2 minus x1, it becomes a vector difference. It becomes r2 minus r1. So hope this is clear to all of you. In case of any doubt, please let me know. So let's look at a quick example.
Sir,
Yeah.
please pull up a bit.
Yeah.
Thank you, sir. Thank you, sir.
Okay. So let's look at a quick example based on this now. So before we get into the example, the distance traveled on the other hand. Yeah.
Can you just hold up for 1 minute, sir?
Yeah. Okay. So that's the difference between displacement and distance. So in general, distance will be greater than equal to magnitude of displacement. If distance is equal to magnitude of displacement, it means that the particle has traveled along a straight line path directly from initial to final position. Okay, so just add this definition of distance, which all of you know, and this quick note about the relationship between distance and displacement. Okay. In general, distance is greater than or equal to displacement. Okay. If distance is greater than displacement's magnitude, it means that the path is not a straight line. Whereas the only situation in which the distance is equal to magnitude of displacement, it means that it has traveled along a straight line directly from the initial to the final position. So in my above diagram, you can see if a particle has traveled like any general path like the dotted red colored path that I've shown, then definitely the distance will be greater than the magnitude of displacement. Only in the situation where the particle travels directly along that straight line, which is the vector arrow s, only in that situation mod of displacement will be equal to distance. Okay, so hope this point is also clear.
So the diagram that you have drawn on the right side
Yeah.
could be in two planars and three planars also. I mean,
yeah, it could be in
2D
2D or 3D also. Like it could be like the 2 points that I've shown are actually lying on the XY plane, like the diagram is actually looking like, because after all, any diagram that we draw, it has to be in 2D because we are limited to the 2-dimensional plane of the screen. Okay, but you can also imagine as if R1 and R2 are not lying in the plane of the screen. You understanding my point now?
Yes, sir.
So the way you could imagine this diagram is just imagine, that XY plane is the wall in front of you in the room you're sitting, and the Z axis is like, or the XZ plane is the floor on which you're sitting. So these 2 points could be anywhere in the room. Okay, so those 2 vectors R1 and R2, they're not lying in the wall in front. They're, they're like this. They're in any sort of direction, which is not necessarily coplanar. So in that
Yes,
case,
sir.
you can see that this triangle that is formed by R1 and R2 and S, it will be sort of in that 3 dimensions of XYZ space. Okay? So we will do an example which will make this point clear. So this is done, right? You have understood these definitions?
Yes, sir.
Yes, sir.
Okay. Okay, so let's move on to an example. So what is happening is a particle starts at time t equal to 0. Okay. First moving towards the north by 30 meters till t equal to 10 seconds. Okay. Then turns 90 degrees and moves towards the west by 40 meters till t equal to 25 seconds. Finally, climbs up vertically by 120 meters till t equal to 1 minute. Take a reference frame such that the XY plane is the horizontal plane with this kind of situation, that x-axis is pointing towards east. So negative x-axis is pointing towards west. Y-axis is pointing towards north. So negative y-axis is pointing towards south. And z-axis the vertical. So if you sort of think of this in 3 dimensions, it becomes like this. Imagine this is a horizontal plane. So gravity is like this. So vertically downwards. So in this plane, what we will see is that the x and y axis lie in this plane. So this is east, west, north, south. And in the same plane, the z axis, I mean, in the same diagram, the z axis is perpendicular to the plane. Z axis is lying like this. This is the vertical direction. So this is the reference frame that the question is asked you to take. Okay. And with this reference frame, we have to now do the following. So find in vector form the displacement S from 0 to 10 seconds, from 0 to 25 seconds, from 25 to 60 seconds, and from 0 to 60 seconds or 1 minute. What is the displacement? Okay. Just take down this question and try out this yourself. Okay. Just to get used to the vector notation and also vector algebra, which we'll be using. Okay, very good, Rishi. That's correct. Akshat, that's correct. Okay. Only thing is, Akshat, you can give the answer in I cap, J cap notation also. Okay. I cap, J cap, K cap notation. You've given the magnitudes, they're correct. Very good.
Okay, sir.
Okay. So what you can first of all understand. Yes, very good. That's correct, Rishi. Okay. So in this kind of diagram, we can understand the same thing, that first the particle is going in which direction? Is going towards north, right, by a distance of 30 meters up till 10 seconds. Then it goes west, but 40 meters. Okay. So if you look at its motion in the first 25 seconds, we don't need to look in the three-dimensional picture at all. We can just understand that it went 30 meters towards the north. Okay. So if it was here at t equal to 0, then it reached somewhere here at t equal to 10 seconds by 30 meters towards the north direction. Thereafter, what happened? It turned 90 degrees towards west and went further by 40 meters and reached this position at a time of 25 seconds. So this is towards west. So now you can understand in this, if we talk about the displacement from 0 to 10 seconds, because my reference frame is such that I'm taking this as my y-axis and this is my x-axis, it is actually 30 j cap in meters. Okay. And if you look at the displacement from 10 to 25 seconds, it is actually minus 40 I cap. So therefore, if you look at the total displacement from 0 to 25 seconds, that is equal to 30 j cap minus 40 I cap. And that has a magnitude of therefore 50, like this. Okay. So that is this displacement in this diagram. This is the net displacement that is happening in that first 25 seconds. Whereas this one is the displacement that is happening in the first 10 seconds. And this one is the displacement that is happening in 10 to 25, like this. Now, the moment we bring the third displacement into the picture, what is happening in the rest of the time, we have to understand in 3 dimensions now, because it's a vertical displacement. Okay, so if this was what was happening, you're going towards north, then you went towards west. So all that was happening in the horizontal plane. Now you're going vertically upwards. So this is my position at t equal to 1 minute. 60 seconds. Now keeping in mind that this is our z-axis, like this, so we can see the displacement from 25 seconds to 60 seconds along the z-axis, so it is plus 120 k cap, and hence the displacement from 0 to 60 seconds, that is the sum of all of these, so it is 30 j cap minus 40 I cap. It doesn't matter what order we write it in. This is the net displacement. So in fact, you can see that this has a magnitude it's going to be given like this. So 130 meter, but the path traveled is much more. Okay, if it's going along these straight lines, you can see the total path traveled is 30 plus 40 plus 120, so that's 190, but the displacement is only of magnitude 130 meters. So this is an example of the application of three-dimensional vectors in understanding of displacement. So I'll just take you through both the diagrams once more. Okay, people, so hope these examples are clear. Now we come to the next vector parameter, which is velocity. As we've discussed earlier about velocity, it is rate of change of position or rate of displacement with respect to time. So when we talk about instantaneous velocity, or simply we just call it velocity. When we just use the term velocity alone, we generally mean instantaneous velocity. So it is defined as rate of change of instantaneous rate of change of displacement with respect to time. Okay, so in a small time dt, the displacement ds will be nothing but dr, because in general we know that displacement is delta r. So in a small time the displacement will be dr instead of delta r. So therefore ds by dt is the same thing as dr by dt. So instantaneous velocity, we can define it as ds by dt, or we can define it as rate of change of position with respect to time. Both are equally valid. Whereas the other type of velocity we define is average velocity. Now, average velocity should be specified separately as average. When we use the term velocity, we generally don't mean average velocity, we mean instantaneous velocity. So that's why we use a separate symbol for it. Okay, so that becomes total displacement upon total time. So this is average velocity for a time interval, let's say delta t equal to t2 minus t1. It becomes r2 minus r1 upon t2 minus t1, because the displacement in that time interval is given by r2 minus r1. So this is the definition of average velocity. So let's look at an example. A particle is moving in the xy plane such that its position at time t equal to t is given by this relation. Where position is in meters and time is in seconds. So we want to find, first of all, displacement at time t equal to t. And from that, we want to find displacement from t equal to 0 to 2 seconds. Then we want to find instantaneous velocity at time t equal to t. The value of instantaneous velocity at t equal to 2 seconds. And we want to find the average velocity from 0 to 2 seconds. Okay, so just go through the definitions above and then apply that to this problem, and it will become clear what we mean by each of these terms. Okay, so let me check out the answers. So let's start with the first part. So what we have to do in the first part is we have to find the displacement as a function of time at time t. Okay. So for the first part, you can see what is the position at a time t in general. It is this one which is given to us, 2 plus 4t plus 2t square j cap. And what was the initial position? This is the initial position at t equal to 0. This is what we call the instantaneous position. That is at the instant of time. So this was, just substitute the value of t as 0. So you will get 2i cap. Okay. So the displacement from this to this time at time t, the displacement is the position at time t minus the initial position. So the displacement at any time t from the initial time becomes 4t I cap. You have to just subtract these two vectors. Okay. So 4t I cap plus 2t square j cap. So this becomes the answer to the first part. This is the displacement at any time t. So therefore now you can see this is at time t. So it means basically from t equal to 0 to t. So for the second part, you have to just substitute. To substitute 0 to 2 seconds. So that is position at 2 minus position at 0. So that in this you just substitute the value of t as 2. You can see it becomes 8 I cap plus again 8 j cap. Okay. So that is the displacement from 0 to 2. Very good. So Rishi, Hitesh. Answers are correct. So this was about the displacement part. Now we come to the velocity. So when we are talking about instantaneous velocity, you can see that we had seen two definitions of instantaneous velocity. One was, two equivalent expressions. We can express velocity as rate of change of instantaneous displacement or rate of change of instantaneous position. So you can see that if I go with the first one, I'll substitute instantaneous displacement as 4t I cap plus 2t squared j cap. If I go with the second expression, I'll express it makes no difference when we differentiate this. So let's also see how we differentiate a vector quantity. So when we are operating differentiation on a vector, we just apply the normal principles of differentiation, treating I cap and j cap like constants. So when you take the differentiation operator inside, it becomes differentiation of 4t, this whole thing multiplied with I cap plus differentiation of 2t square and the whole thing multiplied with j cap. Okay. So next thing you can see when you apply this differentiation of 4t with respect to t will become 4 and differentiation of 2t square with respect to t will become 4t j cap. Now when you apply the same method but use this thing dr by dt, that is you differentiate this, you'll get the same thing. So you can try it yourself. You can use this and you can show that v when you apply the similar kind of steps here, you will get the same expression for v. So this will also help you understand why whether we define it as ds by dt or dr by dt is one and the same thing. So this is the instantaneous velocity as a function of time. So now the fourth part, we wanted to define the value of the instantaneous velocity at the specific moment of 2 seconds. So there what we have to do is we have to just substitute the value of v as 2 seconds. So we will get this as 4 I cap plus 8 j cap in meters per second. This is also in meters per second. T is in seconds. And this displacement is in meters. T is in seconds. So at this specific moment of 2 seconds, this is the value of the instantaneous velocity. And if required, you can find its magnitude and whatever else, right? So now just one part remaining, the average velocity. Okay, very good. That's correct, Rishi. Okay. So now you can see the last part, the average velocity, okay, from 0 to 2 seconds. So that should be the total displacement from 0 to 2 seconds divided by the time interval. So the displacement is, we had seen above, it is 8 I cap plus 8 j cap in meters. Okay, just this value here. Substitute it here. Okay. And divided by the time interval, which is 2 seconds. So the average velocity for that particular interval of time, only 0 to 2 seconds, is 4 I cap plus 4 j cap in meters per second. That's the fifth part's answer. Okay. So as you can see, the application of calculus is very, very simple in these type of situations. Okay. In kinematics, you generally will not require very complicated things from calculus, like application of chain rule or maxima, minima, or something that complicated. It will be simple things like a quadratic equation or maybe a cubic equation or something like that to differentiate or conversely to integrate. So the very basic principles of calculus will be enough. But at the same time, you have to be aware of calculus. Okay. Without calculus understanding and without vectors understanding, the basics of vectors and calculus, kinematics will be of no use. Okay. So that is why in the beginning we emphasize a lot on understanding of basic calculus and vectors. Yes, this is a very good point, Rishi. Let me explain this to everybody. Like calculus and vectors independently, questions will not be asked in JEE because they are maths tools. But kinematics, Newton's laws of motion, and subsequent chapters, they are all part of the core physics syllabus of JEE. So now the kind of things we are discussing, these are like directly the types of questions that you can expect in JEE. So the questions from kinematics that we saw in 1D motion, vertical motion, then today what we are seeing, all these are the types of questions that are there in JEE. Like in your kinematics module also, chapter, you can see that there is, in the end, there is a list of questions which are previous year JEE questions, questions asked in previous year JEE papers. So this is that point from which, that way your actual physics portion starts. Okay. What we did before this was a fundamental base for it. And kinematics has quite a bit of weightage. Like you will see every year in JEE, there are a couple of questions at least from kinematics alone.
Okay, sir. Thank you.
Okay, now the third parameter, which you must have guessed, is acceleration. So displacement, velocity, and acceleration. Of course, position also is there, but these are the main parameters. Acceleration is also now defined as a vector. So the instantaneous acceleration it is defined as instantaneous rate of change of velocity with respect to time. And the average acceleration, though very rarely used, generally we talk about instantaneous acceleration only. So just the term acceleration alone means instantaneous. So this becomes average rate of change of velocity with respect to time, or T2 minus V1 upon T2 minus D1. So for example, if a particle's instantaneous velocity is given by this relation. Now let's take something a little more interesting. So it is given by
बाहर जाना होगा तू ही जाना क्या हो गया
where velocity is in meters per second and time is in seconds. So we have to find instantaneous acceleration as a function of time. And the magnitude of instantaneous acceleration at t equal to 2 seconds. Yes, so that is correct. So we can see that since v is ds by dt or dr by dt, so acceleration, as you correctly pointed out, can also be written as second derivative of displacement with respect to time, or second derivative of position with respect to time. And incidentally, you can also use chain rule, but that will be more for the scalar notation. Okay, so chain rule definition we will not see immediately over here. I will express that to you later when we discuss a little bit more about this. Okay, now let's come back to this. So in this expression, what we have to understand is all these numbers 2, pi by 6, pi by 6, 3 by 2, they are all constants. T is the variable, time T is the variable on the right hand side, and velocity becomes the dependent variable. T is the independent variable. So velocity is expressed as a function of time, albeit it's a vector function because I cap and j cap are also involved. So you can see it's a motion in a two-dimensional plane such that velocity has an x component which is given by 2 sine pi by 6t, and it has a y component which is given by 3 by 2 cos pi by 6t. So to find the instantaneous acceleration, we have to differentiate this. Now I'll just give you a hint that when you are doing this differentiation, you will have to use the concept of chain rule. Okay. Just be aware of that. Be mindful of that when you're trying out this question, that when you differentiate this kind of term, you will have to use chain rule. Because it's not directly sine t, it is sine of something multiplied by t, a constant multiplied by t. So if you recall how we used to do a differentiation of this type, that if you're differentiating sine of 2x, it's not directly cos x because sine is operated on 2x. So this is application of chain rule. That kind of thing you have to apply here. So just try this out and send me the answers quickly.
Sir,
Yes.
sir, in this condition, pi by 6 is not an angle, right? And we don't have to take
It
pi by
is
6 as an angle.
It is actually, if you think of it, its dimension will be in radians per second because t is in seconds, right? So the whole
Yes,
thing
sir.
pi by 6 into t has to be an angle. Okay, pi by 6 into t is an angle. So pi by 6 has the unit of uh, radians per second.
Okay, sir.
Okay. Vineet, beta, pay attention to what I told you that you have to use chain rule over here. Okay. Differentiation of sine t is cos t, but differentiation of pi by 6 into sine t, there is another term that will come. Just like what is differentiation of sine 2x, it is not cos 2x, it is cos 2x multiplied by 2. Because you have to differentiate the term inside also, no? So this becomes differentiation of sine, which is cos, but then multiplied by differentiation of the term which is inside. So that is 2. So it becomes 2 cos 2x. Okay. Just like, for example, if you were differentiating e raised power x square, what would your answer be? Differentiation of e raised power is e raised power, but then multiplied with differentiation of x square. So it's 2x. So it would have been 2x e raised power x square. So this example is not relevant in this problem, but remember that here also we are using chain rule. Here also we are using chain rule. So just try it once more with this thing in mind.
Yes, sir.
Okay, very good. Soham, your answer is correct. So now just apply it to the second part. Okay, you'll get the correct answer. Very good. Your answers are correct, Sean. Now let's work this out. So basically, see, when you're differentiating this term, na, d by dt of sine pi by 6t. So what will happen is this will become cos pi by 6t, okay, multiplied by differentiation of this term, so pi by 6. And similarly, differentiation of cos pi by 6t, this term will actually become minus sine pi by 6t, whole thing multiplied by pi by 6. Okay, so that is why when you express acceleration as rate of change of velocity, and when you apply the differentiation operator to this whole term, you have to be mindful of this chain rule step. This will become 2 times differentiation of sine pi by 6t, whole thing into I cap plus 3 by 2 differentiation of cos pi by 6t, this whole thing into j cap. Now you apply this to over here. So you can see this will reduce to 2 into pi by 6 cos pi by 6t I cap plus 3 by 2 into pi by 6. Sorry, this is minus. Okay, we'll make it a minus. Minus sign. It will become a term like this. It will become pi by 3 cos pi by 6t I cap plus pi by 4, but with a minus sign. I'll take this minus sign outside. So this is the instantaneous acceleration as a function of time.
So we can take the pi common now.
You can take the pi common. Okay. So now you can come to the second part. At t equal to 2 seconds, the value of the instantaneous acceleration will become pi by 3 cos pi by 3 I cap minus pi by 4 sin pi by 3 j cap. Okay. So that will becomes now cos 60 is half, so this will become pi by 6 I cap, and sin 60 is root 3 by 2. So this will become the acceleration in vector form at 2 seconds. So next thing, its magnitude has become this. When you're solving this, you can take by 2 common outside, so you're left with 1 by 2 square, so that's 1 by 4 plus root 3 by 4 square, so correct. So that will be pi by 8 square root of 7 kind of answer. This acceleration's magnitude that we are getting is in meters per second square. This acceleration is in meters per second square. Okay, very good, Rishi. Okay, so like this is a slightly extra tricky type of question, so we'll not worry so much about this kind of thing. But okay, so hope this example is clear to all of you. Now, next we will look at a couple of examples which will help us in the next portion of kinematics we'll be studying very soon, which is projectile motion. So next lecture we'll be totally discussing about projectile motion. So let's do some background work for that. Okay. So now for that we also understand that since velocity is the rate of change of displacement with respect to time. So if you invert this relation, it will become that displacement is integration of velocity with respect to time. And similarly, since acceleration is equal to rate of change of velocity with respect to time, so velocity comes by integrating acceleration with respect to time. So let's understand an example which has this. So a particle starts from rest at t equal to 0 with an acceleration given by this relation, that it is 3 I cap plus 2t j cap, where acceleration is in meters per second square and t is in seconds. This is the acceleration at time t. So what we have to do is, first of all, we find the instantaneous velocity as a function of time. And find similarly the displacement s as a function of time. It's moving in the xy plane. Third, if initially at t equal to 0, the particle was at the origin, that is, then find its coordinates at time t. You can see this is going to be a reverse type of question. Okay, instead of displacement being given from which you can differentiate to find velocity and then differentiate velocity to find acceleration, here is the reverse. Acceleration is given and we have to use the above integration definitions to find velocity and then integrate velocity to find displacement. So see what is going to happen now. There is acceleration along the x-axis. Na? Acceleration ka x component 3 hai, na? So that means there has to be velocity also na, along the x-axis. Yes, Akshat, your answers are correct. Very good. So another way to also understand it is that when you calculate the velocity as a function of time, you can always check your own answer that when you differentiate that velocity, you should get the acceleration. Oh, I think what you have done is you have done reverse. You have differentiated the acceleration, but it's actually reverse. Na? You should get the velocity such that dv by dt is equal to e.
Yes, sir.
Got it, na? So you have just done the reverse of what is required. So Akshat, your answers are correct. Very good. You can try the third part now. It's actually third part is answers there in front of you only because you've written the displacement.
sir.
So so in this, just start with this definition. Okay, that acceleration, velocity is integration of this. Okay, so here your acceleration is given to you as 3 I cap plus 2t j cap. So velocity should be integration of acceleration with respect to time. So now apply this over here. Okay. So when you do the integration, just like in differentiation, you do normal differentiation, treating I cap and j cap like constant. So same thing for integration also. Do a normal integration with respect to time t, but treat I cap and j cap like constants. So split the integration into two parts. Okay, something into I cap plus something into j cap. Okay, so let's look at the conclusion of this question. Yes, very good, Shreyas. Your answers is also correct. So you can see here that if we do this integration, we'll get velocity as 3 I cap plus 2t j cap. This whole thing has to be integrated with respect to time. So we'll split it into two integrations. 3 dt, this whole thing is I cap, plus integration of 2t dt, this whole thing is multiplied with j cap. So this becomes like 3t plus some constant, let's say c1. Okay, we'll eliminate the constant also very easily. 2t's integration will be t square plus some constant c2 j cap. So the velocities of this type. Now we know that at t equal to 0, the velocity should be 0 because it starts from rest. So on the left hand side, we should get the 0 vector when time is 0. So c1 I cap plus c2 j cap. So that means that c1 is equal to c2 is equal to 0. So that means my velocity is 3t as the x component plus t square as the y component. Now you can easily check that this answer that I've got is correct, because if you differentiate this, you will get the correct acceleration, which is 3 I cap plus 2t j cap. So it's just a way of reviewing that what I've done is correct. Okay. And now once I know the velocity, so I'll know that the displacement is integration of velocity with respect to time. So again, the same thing, the displacement will become, I'm directly doing the integration, 3t dt will go with I cap, and e square dt integration will go with j cap. From 3 by 2 t square, again plus some c1 you can say, but c1 and c2 will again become 0 because by definition, sorry, it's t cube by 3, my mistake. Now again, by definition, displacement is 0 at t equal to 0. So you can see that the displacement vector is given by this relation. And you can always check that if you differentiate this, you will get the instantaneous velocity correctly. To differentiate this, you will get 3t for the x component and t square for the y component. So that correctly gives you. So hope these steps are clear to all of you. So it might look a little bit lengthy at the moment because you have this I cap, j cap along with the integration symbols. But once you practice it a couple of times, you'll see it's extremely simple. All we are actually doing here is we are integrating very simple things like a linear function or a quadratic function. So that t square dt type of integration or 3t dt type of integration is very simple really. I cap and j cap are just constant. So if we just get used to using the vector notation while performing a calculus operation, the rest it's pretty simple. Okay. So now also for the third part, we can see that if at t equal to 0, the position vector was 0 because x coordinate is 0, y coordinate is 0. Then at t equal to t, the position vector x I cap plus y j cap will be such that the displacement itself is x I cap plus y j cap. So the x coordinate should be the x component of the displacement. So it should be this. And the y coordinate should be the y component of displacement. So it should be this. So these are the x and y coordinates as functions of time, provided the starting point is the origin. It starts from the origin at t equal to 0. Then at any time t, the coordinates are given by this. Okay, so this is the conclusion of this question. So make sure that you revise today's lecture very carefully And yeah, for some technical reason, I was not able to send you the recording and the notes of the previous lecture. So I'll send both of them together, 3 and 4. Okay. So go through that carefully. And next lecture, we will start projectile motion, which is a very important portion of your syllabus, both from your class 11th internal exams, like board syllabus point of view, as well as from the competitive exam syllabus point of view. So, but you will see that if these basic things that we've discussed today are clear to you, then projectile motion is a very simple application of this actually. Just like vertical motion was a very simple application of uniform acceleration in 1D. Like that, projectile motion is a very simple application of two-dimensional motion. Somewhat simpler than this type of question that we've discussed here. So you should find it quite easy. Okay. That's it for today's session, people. Thanks for attending and wish you all the best. Have a nice day.
Thank you, sir.
Thank you, sir. Bye. Bye.
Thank you, sir.